Albert Einstein, special relativity, E equals mc squared. You've heard all the terms, right? They're some of the most famous ideas in all of science. They completely warped our ideas about space and time and even set a speed limit for the entire universe. But the story of how we got there is just as incredible as the theory itself. So let's dive in and follow the trail of clues that led to one of the biggest ideas ever.
Now that's a pretty bold promise, isn't it? Because we all think of relativity as this super complicated thing. But the truth is, the core idea is built on principles that have been around for centuries. So our mission here is to strip away that intimidating reputation and see how just a couple of simple rules, when you follow them all the way to the end, can completely rewrite our understanding of reality.
Okay, so to really get what Einstein did, we've got to rewind the clock. We need to start with the common sense physics that guys like Galileo and Newton figured out. For hundreds of years, these were the rules everyone lived by.
At the very heart of this is something called the principle of relativity. And get this, it wasn't Einstein's idea at all. It came from Galileo, way back. He realized that if you're in a cabin on a smoothly moving ship with no windows, there's no experiment you can do that proves you're moving. If you drop a ball, it falls straight down, everything works normally. That means there's no special stopped place in the universe. All steady motion is, well, relative.
And you know what? The math that goes with this is stuff you already get. It's totally intuitive. If a bird flies past you and you're walking, how fast does it seem to be going? Well, you just subtract your speed from its speed. It's that simple. Velocities just add and subtract. This was the world of common sense.
This train example really nails it. To Tony on the ground, the plane is cruising at 200 meters per second. But for Bill, who's on a moving train, that same plane seems to be moving slower, only 175 meters per second. Why? Because you just subtract the train's speed. Easy. This was just how the world worked. Simple, logical, predictable. But a huge problem was just around the corner.
Yeah, that whole tidy, common sense picture, it was about to get completely blown up. In the 19th century, scientists were figuring out electricity and magnetism, and they stumbled upon a massive cosmic glitch in the system.
Think about it. What if there was something out there whose speed wasn't relative? What if there was one thing in the universe whose speed was always the same for everybody, no matter how fast you were moving towards it or away from it?
Well, that's exactly what popped out of the equations of this genius, James Clerk Maxwell. He put together all the rules for electricity and magnetism, and buried inside them was an absolute bombshell. The speed of light, which we call c, is a constant. It doesn't care if you're in a rocket ship chasing it or running away from it. You will always measure its speed to be the exact same number.
And right there, you have a massive, massive problem. Let's say your spaceship is zooming along at 2/3 the speed of light. Newtonian common sense says that if a light beam passes you, you'd measure it going at a slower, relative speed. But Maxwell's laws said nope, you'd still measure it traveling at its full, breakneck pace. What of them had to be wrong?
So you've got this huge paradox. What do? Well, the scientists back then didn't just throw out centuries of physics. No way. Instead, they tried to find a fix. Their solution was to invent a weird, invisible substance that filled all of space, something that light waves could travel through. They called it the luminiferous ether, and wow, the stuff it had to do was just bizarre. It had to be absolutely everywhere, but also totally invisible and massless. It couldn't create any drag, or else the planets would have slowed down and crashed into the sun by now. But at the same time, it had to be more rigid than solid steel to let light travel so incredibly fast. It was basically a ghost.
Okay, so the thinking went like this. If this ether stuff is real, then we, here on Earth, must be flying through it as we orbit the sun. So two brilliant scientists, Michelson and Morley, designed this incredibly sensitive experiment to detect that motion. They were looking for an ether wind by measuring tiny differences in the speed of light.
And the result they got, the big, game-changing number they measured was 0. A big fat nothing. No difference at all. No matter how they turned their machine, no matter what time of year they tried, the speed of light was stubbornly, frustratingly, always the same. There was no ether, and now the mystery was deeper than ever.
So physics was totally stuck. And the solution didn't come from some world-famous professor at a fancy university. It came from a 26-year-old patent clerk in Switzerland named Albert Einstein. In his spare time, he came up with a completely new, incredibly bold way of looking at the whole problem. Instead of trying to force one theory to fit the other,
Einstein did something, well, kind of mind-blowing in its simplicity. He just decided to believe both of them. His first rule, or postulate, was that Galileo was right. The laws of physics work the same for everyone. His second rule was that Maxwell was also right. The speed of light is constant for everyone. His genius wasn't in some crazy new math. It was just in having the guts to ask, hey, what if they're both right, and it's our common sense about space and time that's wrong?
And here's where things get really wild. Because if you just accept those two simple rules as true, the consequences are, well, they're unavoidable. And they completely shatter our picture of reality. It turns out, our universe is a whole lot weirder than we ever imagined.
The first big consequence is that time isn't a constant tick-tock for everyone. For the speed of light to be the same for everybody, it means that moving clocks must run slower from the perspective of someone standing still. And this isn't a trick. Time itself actually stretches. We've proven this. Tiny particles called muons are created in our upper atmosphere. They should decay long before they reach the ground, but because they travel near the speed of light, their internal clocks slow down so much that they actually make it all the way down to us.
But hold on, it gets even weirder when you flip your perspective. From the muon's point of view, it's not moving. We are. So its clock is ticking just fine. So how does it make it to the ground? Well, from its perspective, the entire 10 kilometers of atmosphere rushing towards it gets squished, it gets shorter. So what we see as time slowing down, the muon experiences as distance shrinking. Both are correct. It just depends on your point of view.
And all of this leads to maybe the most famous equation in the entire history of science, connecting two things we never ever thought were related: energy and mass.
So what does that actually mean? Well, that c² is just a ridiculously huge number. It's a conversion factor from hell. It means that mass is just an incredibly, unbelievably concentrated form of energy. Take just 1 gram of matter, about the weight of a paperclip, and if you could convert it all to energy, you'd get 90 trillion joules. Mass and energy aren't different things. They're two sides of the very same coin.
So let's wrap this up. By starting with just 2 simple rules, Einstein showed us that our bedrock concepts of space and time aren't fixed at all. They're relative. He showed us that the speed of light is the ultimate cosmic speed limit, and he revealed that mass is just a hidden form of energy. He didn't make things more complicated. He just revealed a deeper, stranger, and way more elegant reality than we ever knew existed.
And that just leaves you wondering, right? If a young patent clerk, just by taking 2 simple ideas seriously, could completely upend centuries of science, what other basic things that we think are common sense might be totally wrong? What other cosmic glitches are just sitting there, waiting for someone to ask the right question?